After a very interesting talk from James, really on the basis of Python, introducing us into many very interesting concepts, we are now coming a little bit more up from the machine room and have more application-oriented perspective on Python. Those of you who might have attended my tutorial on Friday, they know me already. I will say a couple of words about me in a minute. While my tutorial was more about interactive analytics, this talk is about derivatives analytics, which is a little bit more involved in terms of what you need in terms of mathematical finance and stuff like that. Nevertheless, all the examples that I will present today are in an interactive fashion, but the underlying machinery that we use is kind of a very class object-oriented approach that I've implemented. I mean, there's almost for everybody, for anything, there is a library available in Python, but not yet one to do honestly derivative analytics. So what this talk is about. I would start with a brief history of relevant finance research for what I will be presenting. I will briefly go into the differences between analytical and numerical option pricing, then touch upon, of course, Python for derivatives analytics, give an overview of the library, and also provide some selected use cases from more simple one to more complex one, up until to the calibration of different models. Those of you who have seen me already or met with me might know that I'm Managing Director Europe of Continuum Analytics. I founded Physician a couple of years ago where we started using Python immediately. So I do this, applying Python to the derivatives analytics arena already since almost 10 years. I'm lecturing mathematical finance, also, of course, using Python. You might have seen my book, Derivatives Analytics with Python. And currently, I'm writing the book for O'Reilly, Python for Finance. Has also a little bit of derivatives analytics, but not too much. And my background actually is in derivatives analytics. I wrote about dynamic hedging strategies and the impact on volatility in financial markets. As always, when I give a talk, you find the slides hosted on my private website. So if you want to go to that, hilpisch.com, you see the URL there. I tweeted also the link. So if you go to my Twitter handle, DYGH, you will find the link as well, and then you can follow it or see what's going on in here. A brief history of option pricing research. There is a little bit of history. So actually, as we know of today, it started already in 1900 when a French guy, Bachelier, handed in his PhD thesis and was researching a couple of years about the topic of option pricing. Actually, at a time when nobody has had the terms that we have today, like arithmetic Brownian motion. This is a term which was coined pretty much later. But nevertheless, at that time, the mathematical construct was of high interest. So Albert Einstein, wrote a famous paper at that time in his Annus Mirabilis, 1905, and provided first original theory for Brownian motion, which is kind of the cornerstone, the major building block of today's mathematical finance. Samuelson later rediscovered these approaches, first introduced by Bachelier, but was never able to really come up with a closed-form solution, getting rid of any ad hoc element. This is actually due to Black-Scholes Merton, who partly collaborated but published two papers in 1973. As most of you might know, later two of these guys were awarded the Nobel Prize for Economics. One was unfortunately passed away already at that time. Merton then published, for example, a paper adding jump diffusion, which are quite popular. And already in 1977, someone proposed to use Monte Carlo simulation for the pricing of European options. I mean, at a time when there weren't these computers that we have heard so many fantastic things about here at this conference available. But still, the method was introduced, and later on, the research team, Coxworth-Rubinstein, also introduced a pretty efficient numerical method also to value American options. It's not only the binomial option pricing in terms of numerics, but with their approach, it was also able to value efficiently American options for the first time. Later on, a couple of very interesting things. I want to highlight the first bullet point here. Harrison, Krebs, Plisker. At the end of the 70s, they came up with the general risk-neutral valuation approach, today's so-called fundamental theorem of asset pricing, where they used the machinery of martingale theory to provide something for a general market. I mean, when you think of Black-Scholes, there's one risk factor, there's one product, this is a pretty simple world. we don't live in this simple world. We have a much more general world where we have many, many risk factors. Recently, when I heard a talk of analytics head at Morgan Stanley, they said they simulate 500 core risk factors and 20,000 others for the risk simulation. I mean, this is the market that we have. We don't have a single one. We have many, many risk factors and many, many products. And the number that this guy mentioned during the presentation was 3 million positions to be valued per day. So we don't have a single risk factor and a single product or a single trade. We have many, many risk factors and many, many trades. And this is actually, in theory, introduced already at the end of the 70s. Later on, there came a couple of models that generalized in some direction. Existing models like stochastic volatility was introduced by Heston in a systematic fashion. He also introduced Fourier-based option pricing to the financial world. In that case, we had Bates who combined the jump diffusion with the stochastic volatility. And maybe worth highlighting is the Longstaff-Schwartz paper in terms of that it for the first time provided an efficient algorithm to value American options, which has been around almost since 100 years at the time, with Monte Carlo simulation. So it took quite a while to come up with an efficient algorithm to value American options so heavily traded by Monte Carlo simulation. And this was kind of a breakthrough that allowed for many, many more analytical advances later on, actually. What is the main difference between analytical option pricing and numerical option pricing? The famous Black-Scholes formula, as I said, has a single risk factor, 2 traded assets. The one is a risky one, is an index or is a stock, described here by the geometric Brownian motion. And the other one is kind of a riskless bond or a cash account. You can think of it that way. In this simplified model, they were able to come up with this closed form solution where you say, well, I have a couple of input factors, I put them in here, and then I get a price for my option. For the first time, no ad hoc element. It was a model, and the closed form solution was the result. And it was, even at that time, pretty easy to evaluate this function. Later on, there came out like Texas Instruments calculators that had like implemented this function. So you only provided kind of the input factors, and the calculator on your desk gave you the price for the option. So this was the state of the art at the time. Very efficiently, you don't need any kind of sophisticated or high-performance machines to solve that. If you want to implement it in a class-based, object-oriented fashion in Python, it might look like that. I mean, there are a couple of other ways to do that. This is a self-contained fashion. You have a couple of input factors here, attributes of the class, of the object, and you have, in principle, only one method, which provides the present value. It is the calculation of the formula in that sense. Once you have instantiated such a class, you have your object, which I call here call. I can call the method present value on this object, and I get back, in a very simple fashion, my option price. In this case, you should remember the number is 10.45. So pretty simple, pretty easy. 5 input factors, 1 output. The beauty and, I mean, the main reason for why almost everybody is always looking for analytical formulas is that it is pretty efficient. Here you see I value 5,000 different options, and on this MacBook Air, it takes roughly a little bit more than a second to evaluate all these options. I mean, this is quite efficient. I mean, 5,000 options on this notebook to be valued. I mean, the bank would be happy if this would be the case for every trade that is in the books. Unfortunately, it is not, because the majority of trades is not as simple as the stuff that we see here, nor is the world that you have to model, that you have to take into account, as simple as the model proposed and introduced by Black-Scholes Merton at the time. On the other hand, the Monte Carlo simulation alternative, what does this mean? Actually, this means that we work more with approximations, estimations, based on generally a large number of simulations. A large number of simulations in the sense that I choose a capital I, which might be 100,000, might be 1,000,000, to simulate the paths of my index or stock level given a discretization scheme of my differential equation. So this is a numerical method. And this is pretty computationally demanding. We see we have log functions, we have squared, we have additions to do, and if you want to do this 1,000,000 times or even 100,000 times, this leads to quite a different computational burden, giving actually the same problem in this case. But let us have a look how this could look like in Python. Here, again, a pretty simple class-based implementation of the same problem, but now using Monte Carlo simulation as a numerical method. You see here there are two methods right now. I separated the path generation from the valuation effort here. So here this method generates all my paths, given a certain number, maybe 100,000 to stick with this particular number. And the second method calls the first one, gets back the paths that are generated, and then calculates a net present value and gives this back. So it looks pretty similar. We have an additional method, but in the end, the same attributes. I have to give and a couple of numerical parameters, in this case, M and I. But I mean, this is quite the same thing as expected. I mean, we're working in the same financial world. So the call and the instantiation is almost the same. I instantiate my class, get back an object, which I call now call Monte Carlo simulation, and when I call the method present value, I get back a present value. This is not exactly the same, but as expected, I mean, we're using a numerical method. I said that before. We have an approximation of the value. So this is not precise in a certain sense, but I mean, it's pretty close. So I wrote here already quite good. What we can do, of course, is throw more computing power to that. We can add paths to that. We can say, well, 10,000 paths might not be enough. Do 50,000 paths. What we see before, it took like 50 milliseconds. Now we have already 300 milliseconds for a single valuation. If we now say, well, I can also control for precision by hiring the number of time steps, the time crit that I use to approximate my differential equation for the simulation, I see, well, I come pretty close to the 10.45 in this case, but it already takes 3 seconds. Just to compare it, 5,000 valuations in roughly a second, using Monte Carlo as a numerical method. For a single option, 3 seconds. All on the same machine. I mean, you have to judge these values in relative terms. If you do it on a separate machine, maybe using parallel execution and stuff like that, then the absolute numbers change. But still here, ceteris paribus, there's a huge difference in performance. But then you would say, well, how care? I have this perfect method where I can value 5,000 options per second. Why should I care about Monte Carlo? I mean, Monte Carlo is a much, much more flexible method, but a little bit more about this. This chapter called some general considerations. There are potential problems with analytical formula. I mean, as I said, with the Texas Instruments calculator, even everybody not working in the finance industry can calculate via this black box approach an option value, I mean, without knowing anything. But on the other hand, if you're an expert and you understand it fully, this is still the case that there are limited, only specific use cases. There's also no consistent value aggregation in the sense that if you value different options with different models, different parameters, what is the point in adding these up when there are, for example, correlations in existence? And you have to model different underlyings. No consistent risk aggregation. I mean, risk aggregation, value at risk, credit value at risk, and stuff like that, and netting operations, is very important to have the full distribution, which is not provided here. We only have a point estimate. We're only working with the expectation parameter, with nothing else. And the last point emphasizes this again, no incorporation of any kind of correlation in that case. But of course, we have advantages. So, I mean, that's the beauty of the analytical approach. It's easy to understand and apply. I see a formula, I put something in, I get something back. In general, we have high speeds for the numerical evaluations, low technical requirements. You can do this on even the smallest machine, on a Raspberry Pi, you name it. There's actually no problem at all. And it's also easy to test and implement. Alleged drawbacks of alternative numerical methods, such as simulation, I mean, they are compute intensive. We have seen that. 100,000 or even 50,000 paths with 500 times. This is already a computational burden. Of course, there is a memory demand which arises out of this. We have accuracy issues which we have to control for, conceptual problems, for example, American exercise. This is much more involved than European exercise in this case. And we also have implementation issues. It's a little bit harder typically to implement numerical methods compared to just kind of a closed formula. Testing and maintenance, like test coverage, for example, are also typically more complex. But on the other hand, and now we come to the point why the whole world uses it right now, it is highly flexible and powerful. You can use almost any model with the numerical method, any derivative, any portfolio. Compared to the Black-Scholes world, you have only this one single model for the underlying, and you can apply it only to a put or call option. I mean, this is very limited, given the millions of different products and trades we have in the world. This is a very limited scope. We have a full distributional view. When you think of risk, we have all the frequency distributions for everything you can think of. We have consistent value aggregation when we use these methods consistently. We have consistent risk measures because we have full distribution and not only first-order approximations which are used in some cases. Also consistent estimation of netting effects, pathwise, namely. It's very granular how you can implement these techniques. Consistent incorporation also of time-varying correlations maybe, and last but not least, full graphical analysis, no black boxes or even small corners of the algorithm. Here, just to illustrate it, this is the data I have generated by the Monte Carlo simulation beforehand. You can inspect almost any value. This is one of the most simple examples you can generate. This is the frequency distribution, the full distribution of the simulated values at the end of our time period that we consider. So you have a look, or you can have a look into every single data point. No black boxes, nothing behind the scenes in this case. I mean, you have to judge all the things that you see today against the background of technology advances. I mean, when I wrote my PhD thesis, fortunately at the time, I wrote a theoretical one, so I didn't need a computer apart from writing it up and publishing it. I had only a couple of numerical examples, but if I would have liked to implement, for example, Monte Carlo valuation, it would have been much more hard to do than today. At that time, you had single-core computers, only low-level programming languages available, like C and Fortran. So it would have been a high burden to reach some kind of high performance or acceptable performance. It would have cost me much more than I would have had probably at that time as a PhD student. But today, it's even for, yeah, let's say, not well-equipped PhD students, not very rich ones, maybe coming from a good background, it's pretty simple to rent like one machine after the other on cluster structures or whatever. You have many cores, large memories, powerful GPUs, even on your local machines. You have high-level programming language, which allows scientists today to implement even the most complex algorithms quite efficiently. And you have low, and I think variable might also be a very important factor, cost for even large machines. So you can scale, you can buy computing power for one day as a researcher and say, well, I did all my calculations, fine, now I'm done. I mean, times have changed, and even more so for banks who have large budgets and business cases to support such infrastructures or exchanges to this end, of course, as well. DX Analytics, what is it? What is it about? We come now to the core. It's based on general risk neutral valuation, what is typically called in the practical world global valuation. Which means that you model your risk factors only once, non-redundantly, and then on top of that, on the simulated world, you value your single trades or products. Monte Carlo simulation is the only numerical method which is able to cope with such a world in terms of valuation. And Creek's Fourier-based formula, which are pretty fast for calibration purposes. You can have arbitrary models. It's pretty flexible. Single and multi-risk derivatives, European and American exercise. It's completely implemented, the library, in Python. And hardware is, in that sense, not a limiting factor. You can easily scale it. Global valuation at its core means actually non-redundant modeling. You model risk factors only once. You have consistent simulation, for example, in terms of the given correlations that you assume. You have, in the end, as a result, consistent value and risk aggregation, which allows you really to have a clear and consistent, economically, financially consistent view on your positions. And you can zoom in on single positions, but you have also a consistent net view on the portfolio, on the whole portfolio, on the trading book. Python specifics, I have only 3 points here. It's not like that I use some magic things here. Of course, heavy use of classes and object orientation. NumPy and the array class, mainly also pandas, data frames and stuff like that for numerical data. And Python dictionary are heavily used for all metadata. So the accessing time and efficiency of Python dictionary is, I think, one of the major strengths that you can apply here in this case. Some simple example. It's a library, so from the xlib valuation, I import everything. Start by discounting. So for example, it's the most simple class, it's the constant short rate class. So I instantiate a discount object, if you like, a short rate object with 5% discounting rate. I have a time list here in this example. I start at the middle of this year, go to the end of the year. This could be any time list. I just generated it using pandas for convenience. I provide this time list to get back the discount factors. Maybe the naming might be a little bit confusing, so I wrote here a remark in that it's the price of unit zero coupon bond values. So the classical way of discounting in derivatives analytics, which means at the end of the horizon, the price of the unit zero coupon bond is 1, and you have the net present value of this bond today, and using the factor of 0.97 allows you to discount from the last date to this date. And the discount factors in between have to be calculated given the current values at this particular date. You can also provide, apart from PyData objects, you can provide, which is usually done in theory, also year fractions. So they say half a year from now, for example, which would be reflected by 0.504 in this case. So you can go two ways, but I try to do it as Pythonic as possible, so using PyData objects and all the typical things that you would expect from a Pythonic derivatives library, but this might be more geared toward researchers or academics. A market environment. Of course, we are not like in a theoretical world. In the ivory tower, there is a market around us. So for example, here I start instantiating a class, an object for a jump diffusion. JD stands for jump diffusion. I just give it a name and the pricing date, and you see here this is indeed kind of a beast out of my library, and it's called market environment, so a very specific beast which I can now fill with the relevant values, like the initial value of something, volatility, lambda. You don't need to understand all the single details. We'll see the results later on. But in the end, I provide everything similar to the Black-Scholes example before, that I need to value derivatives based on my market, based on my environment. You see I add a couple of constants. These are single values, could be a string, for example, for the currency, or I provide other objects, curves, more complex animals that live in this world. In this case, it is the discount curve R that I have instantiated before. Now we come to the model. I mean, the whole thing is geared towards pricing derivatives and doing analytics on that. So we have to have our underlying, our risk factor. In this case, we only have one risk factor, which is called JD for jump diffusion. You see this is a class out of the library. And this class has attached a couple of methods. Here in this case, for example, get instrument values. And the instrument values are like the results of the simulation procedure that we have seen before for the Monte Carlo case of Black-Scholes, and I just print out here the last values. These are the values you see -1 for the last column in my array, and you're getting the simulation results, the single ones for the last date for the majority to value the option at hand. So you can, of course, plot everything, and you see the typical behavior of a jump diffusion. I assumed a large jump size that you can detect the jumps quite easily. You see, this would be more like the typical geometric Brownian motion. This is like moving with a certain volatility and with a certain drift. But here you see the jumps occurring with a certain probability over a year, or here in this case over half a year, and also with a certain jump size which is distributed log normally. So there are variations in the jump size. This would maybe reflect some crises or bad news for a stock, for example, disappointing in terms of earnings expectations. Now the option. For the option we need as well a market environment. This one is pretty easy. The only thing that I provide here is the currency. We have already assumed the majority of parameters that we need. And you see here I instantiate the evaluation class for the call that I want to value. I give it a name. I give the market environment. I provide the underlying risk factor for this single risk valuation class, and I provide in Pythonic fashion. This doesn't have to be, but just to illustrate how it works internally, I provide in Pythonic fashion the payoff of the option, which is a standard payoff for a call option, which means the maximum of the value of my underlying at maturity minus the strike price. Here in this case is 100 and 0. So it's a typical payoff for a European option. Pretty simple. This is actually the same that you could value with Black-Scholes model, but in a Black-Scholes model we couldn't include the jump component. This was done later by Merton, though this reflects the setup of Merton 1976. I have now a couple of methods that I can call the present value. Of course, this is maybe the most important thing, but for trading and risk management purposes, you might be even more interested in the delta or the vega, which is the first derivative with regard, here in this case, a numerical derivatives with regard to a change, a small change, a marginal change in the underlying, or a small change in the volatility of my risk factor. We can do a little bit more analytics. People like to have it visually, so we go over a couple of prices, a couple of starting values, if you like, for our underlying. And what we see here, we see different present values, of course. For a call, here the call is much in the money. We have a high value. You see the typical delta structure coming from close to 0, approaching 1 at a single time. And here we see the spiking vega around the strike price. So you can do similar things that you are used to do with a closed formula, like the Black-Scholes one. There are a couple of others, but it's the most popular one. You can do here in quite a similar fashion, but the underlying implementation is completely numerically based in the sense that we only use Monte Carlo simulation for all the things that you see here. Now, a little bit of a more complex structure. What we've seen so far is pretty easily implemented. You can even write it up when you're a bit experienced. You can open your IPython notebook and write your difference equation and simulate it and come up with a price. But you want to have something maybe that is a little bit more general. So we do something with multiple correlated risk factors and also with multiple derivatives, so that we come to at least a more realistic case. You could think of kind of a larger hybrid trade that the bank wants to implement with a couple of derivatives, or a hedge fund, which is a little bit more complex. This doesn't resemble kind of a trading book of a bank, but it's more like a complex trade that you could encounter in a hedge fund or in an investment bank. So once again, this is pretty similar. We have our short rate object. There are others available, but I stick with the simple one that we have here. We instantiate 3 different underlyings now. I will skip pretty quickly through these. We have a geometric Brownian motion in this case. We have a jump diffusion that we have seen before. And we also have something with stochastic volatility. Here in this case, there we need a little bit more. We need vol, kappa, theta, rho, lambda. No, lambda is not needed because we don't model the jump diffusion. We only use the stochastic volatility part. So we have 3 different risk factors which are based on 3 different popularly used models in finance. All the things that are common to the market, I collect in a valuation environment, and I add the valuation environment to every single market environment of my underlyings. So this is pretty simple. It's kind of an inheritance, so to say. Once I have defined the major metadata points, I can provide them to every single market environment that I've written up. Here in this case, it's kind of the last step to finish the modeling of the market. I say, well, given my market, what are the underlyings? This is a dictionary, as you can see, and I provide the correlations as a list of a list. So I assume 2 correlations, one between the geometric Brownian motion and jump diffusion, which is positive, and one between the jump diffusion and the stochastic volatility, which is highly negative in this case. Now the derivatives. I have a simple one, American put option. I have to provide a couple of information once again. This put option is based on my geometric Brownian motion. Here in this case, I can, without thinking of portfolio or adding all the things up, I just can simply value this single option, in this case an American option, by providing, again, market environment, specifying the underlying and providing the payoff. and I get back here, in this case, the net present value of my option, which is in this case 4.49. Now, it gets a little bit more involved. We have the European maximum call on two assets. Now we will have two underlyings, two risk factors. Once again, I need, of course, a market environment. Nothing exists on its own. I have a market that I have to take into account. Here in this case, you see, of course, the payoff of this call actually will include two different underlying values. It is the maximum of the two relevant risk factors, but apart from that, it's actually the same. Here in this case, to just value the single option, I define kind of a subset of a market. I say, well, these are the two relevant assets. The correlations are the one that I've defined before. I have here a valuation object, which is now called or instantiated from the class valuation, Monte Carlo multi-European. Becomes larger because it becomes more complex. And in the end, it all works the same. Once I have this beast, I can just call the present value method and get back in the same fashion as I was used to, for example, when using Black-Scholes, my value for this more complex object. Now I, of course, have two deltas if I want to calculate them, one with regard to the first risk factor, one with regard to the other risk factor. So the world, as I said, becomes more and more complex, not only one delta, two, and of course I have also two Vega components here. What I now do here is a, let's say, 3D visualization of all the stuff that I've done. The code is not that relevant, but what we see here, when we plot the present values, you can see the present value independence of the two risk factors of my two underlying objects. What you can also do is to visualize the creeks in 3D. You see the delta here in this case with regard to the geometric Brownian motion, and on the other hand, the delta, the derivative with respect to the initial value of the jump diffusion on the other axis. So you can do like of more complex analytics with the derivatives, but in the same fashion, once again, as you might be used to using analytical formula. This is the delta now for the jump diffusion. Looks a little bit different, but you have just to change the orientation, then it might be give you this, a similar impression. You might notice this is more like you see from the one side into it, and here you see from the completely other side on the thing. But nevertheless, you can do analytics once again in a very compact fashion, providing all the different risk factors that you need to hedge and to manage your positions. Last but not least, the same thing for Vega. Here we have the Vega with respect to the geometric Brownian motion, which has a spike around the strike over here, which behaves a little bit different here in this case in the jump diffusion direction. And once again, we see the same thing, but now the Vega with respect to the jump diffusion with a different orientation. You now have the spike of that over there. Again, at roughly 34, which is the strike in this case. Now to make it a little bit more complex even, a minimum put on two assets, but now with American exercise. Now it gets involved. We have multiple risk factors. And we have American exercise. This is already kind of a tricky numerical thing. But the whole thing, details are not that important. Payoff changes, but the whole thing is mainly the same. You can value it on a standalone fashion, similarly to the most simple one as before. You have your Vegas, your deltas, and everything are the same. Once you have this object, it behaves like the most simple one that you can conceive. So all is quite similar. But now we are coming to the more interesting part, putting all the things together, doing one market, one trading book out of it. To this end, we define three derivatives positions, another class, which is called derivative. There are a couple of differentiations right now. The most important one is, of course, that you might have different numbers of the single object in it. Here in this case, to make it simple, I have 2 of the first one, 3 of the second one, and 5 of the last one that we have seen to make a difference between the single positions. And you can add this to a portfolio. You say right now, well, these are my positions. Now make a portfolio class out of that. Put all the things in that, my positions, my valuation environment, all the underlyings that I have, and the correlations. This defines now my market, and in the end, with the positions, also my portfolio. And what you can do, again, in a very simple fashion, by a single method call, you get a statistics. This is kind of customizable. You can add in here whatever you like. This is just a formatted printout using pandas. You get information about all the things that you have now in here. You have this position, this is the name, the quantity, the value of a single thing. Here is the position value, which means multiplied by the number of products you have in there. The two deltas and the two vegas, if there are two. But what is noteworthy in this environment, you have to remember maybe the 17 and the 23, roughly 40 together. We would see the effect of changing the correlation, actually. But again, you have portfolio. This is already 3 risk factors, 2 rather complex products, 1 mainly standard product. But you can easily add up, and you have a consistent risk and value aggregation in this case. In this case, where we have seen the statistics before, we have a high correlation, high positive correlation between geometric Brownian motion and the jump. No jump occurs here in the blue line, and you see they move pretty closely, a pretty similar behavior. If we now change the correlation between the geometric Brownian motion and the jump diffusion to minus 0.7, we see also change in the values. And I mean, this is what everybody's interested in. If you model the market right, what are the effects, not only the net effects, but also single effects, given my portfolio? Before we had 17 and 23. It's roughly 40. It was roughly 40. Now we see correlation changes. The net value of my portfolio doesn't change, but we see a change in the single values because we have correlation options. Minimum and maximum options of multiple assets are nothing more or nothing less than correlation options. And you see here with this approach, with the library, you can easily take into account every single element. And of course, as I said before, you can also inspect what is happening. This is exactly the same path that I've shown before. See this movement, but now we have this highly negative correlation, and you see exactly how the market is now modeled and how it evolves numerically in this particular case here. So it's very, very granular. You have a rather general approach called global valuation. Just to give you an idea, I mean, I've been working in kind of a laboratory environment. I mean, I assumed a couple of parameters, like an initial value, volatility, and stuff like that. This is rather academic, but of course you want to price your options in a market-based fashion, which means to reflect what the market is giving you. And this is usually then an exercise of calibrating the model. Those of you who have attended my tutorial on Friday might remember that I have done a little bit of work with volatility derivatives. I just want to show right now, as a last example, how you can calibrate a model that is provided by the library to real market data and to replicate option prices. Only a couple of imports. I need, of course, data to calibrate to. This is data from the last trading date of 2012. A little bit of instantiation. I need to provide a couple of data to this model. It's a more complex one. I have specific classes for the calibration. Here in this case, it's called SRJD calibration for square root jump diffusion calibration. And the first thing I do here in this case is do a term structure calibration, which means I take all the futures prices and first calibrate my futures curve. The model doesn't provide too many degrees of freedom to resemble the of sophisticated structures, but you see this is kind of like a regression approach through this, and the differences are taken into account later on when I value the single options. So it's the first step. Global optimization. I now have a set of parameters, 6 to be specific, which I can use to calibrate the model to the market. And here you see a global calibration procedure. It's not too long, takes a couple of seconds, and I have a first result. Here we have the mean squared error of all my 39 option prices in this case. But global calibration might not suffice. I can go one step further. But first, the results here. Here you see what calibration means. We have the market data, which are the blue lines, and we have the red dots, which are my model prices. So what I want in a perfect model world. I want to perfectly replicate my market by my model values. I mean, then I have the perfect model. If I would have this for every market, I could make huge amounts of money. Here you see we have still quite huge differences given our market prices. So we have to optimize the calibration itself by local optimization. And here you see I do 100 runs, which is not too much, but it takes quite a while. Here in this case, almost 2 minutes, but there's no parallelization. It's all done here on my machine based on Monte Carlo simulation, I must confess, so to say. This is a numerical calibration approach. I've implemented this also in parallel, and it scales quite linearly with the number of cores involved, so there shouldn't be a bottleneck if you have more complex problems. But let's see how good we can become. And you see here it's becoming much, much better. We are much closer here on the prices. This is the last maturity date of the VStocks options. In this case, it was August 2013. This is the shortest maturity, which was January 2013. But you see the calibration fit is much, much better than we had before. So the library, in essence, provides everything from the modeling of the most simple objects that you might face in the market up until calibration. I will skip this. This is a little bit of background. So we've been working on this since a couple of years. We've also written up a derivatives analytics library, which we provide via a web-based delivery approach. You find it under derivativesanalytics.com. There you can register, for example, for a free trial. To have a summary about the X analytics, it's Pythonic. Completely based on pandas, NumPy. There's no specifics. I mean, if you're used to Python, you might be up to speed pretty quickly. It's pretty flexible, you've seen. You can model many, many things, multi-risk, single-risk, complex structures you can calibrate. It's consistent in a sense that every single data point is aggregated, is netted in a consistent fashion. It's easily enhanceable. I mean, it's object-oriented. You can add new models on the fly if you like. New features can be added on the fly. It's performant. Performant here in this case means for standard Python, I've used all the techniques that are available. There's no parallelization or whatsoever included right now, but this is easily added as well. It's pretty easy to integrate it. For example, if you think of solutions such as Data Nitro, which allows you to script Excel, you can easily implement like an Excel spreadsheet as a front end and use the library to model your derivatives and to value them and to do portfolio analytics or whatever you might want to do, and using Excel in that sense as a graphical front end for the library. And it's open. I mean, due to the use of a market environment approach, you can connect with any database. Thomson Reuters, Bloomberg, you name it. Any database can be integrated. You need only simple wrappers where you get your data out of your data provider's database and put it into the valuation procedure. The last thing I will skip, but it's one of my standard slides, why we should use Python. I mean, the library is not that large. It was able for me to write it up personally as a pet side project. I mean, this says a lot. I mean, in banks there are like hundreds or even thousands sometimes working on similar stuff. So Python is, I think, the right language, the right technology environment or platform to accomplish these analytics goals in a sense. Thanks.
I might have missed it, but whenever you're pricing up your assets for a product, do you input a vol surface or just a single vol number?
It depends on the only type of models that have been shown is a parametric model. So I've used, for example, a stochastic volatility model, which you could calibrate by itself, for example, to a vol surface. In the last step, where you've seen the calibration, there I used, if you like, to the vol surface to calibrate the model and to value the options in that sense.
With the Monte Carlo and structured products, you might want to use local volatility. So that would mean your simulation's a bit more involved.
I don't have shown any local vol example today, only parametric models in the sense that we're working with like the economic parameters and not the numerically fitted to the market. But it's the procedure and the approach would be exact the same. Only the underlying mechanics would a little bit shift, of course. There was another question. Yeah.
You saw the vega for the simple black, so it's a GBM process, and then you have the vega for the stochastic volatility process. how do you get the second one? Because there's no direct volatility input there. You get the dV over the sigma from the GPM, and then you get the vega from the stochastic volatility. So my question is that there is a...
I haven't shown the values for the graphics that we've seen was for the geometric Brownian motion and the jump diffusion. They, of course, have the single wall parameter.
And the last one, you have an SV model in the more elaborate example, you have a best of, worst of, and something vanilla.
Yeah.
I mean, maybe I missed something on the way, but I think that's what you saw.
Yeah, but as I said, the graphics were not with regard to the stochastic volatility, and you're right, the last example included, the last example where I haven't shown the graphics is included. In that sense, I have standardized the input parameter to shock the original stochastic differential equation or difference equation. Even though you can take the vol parameter or the initial volatility, and what I do is to shock the initial volatility for that, or the initial variance, if you like. So this is what I shock in this case. If you would like hold the stochastic volatility part constant, you would end up with a Black-Scholes model, in a sense, and this is what I shock in this case.